The International Space Station is about to disappear forever. After 25 years of breakthroughs, this giant laboratory, built piece by piece in orbit, is now heading toward its final chapter. And yes, there's already a plan for how it will be destroyed. In this video, we reveal why the ISS must retire, how engineers will guide it into a controlled dive toward Earth, and what humanity loses and gains when our greatest outpost in space takes its final orbit. Building the impossible. The International Space Station exists because nations dared to attempt something no single country could achieve alone. The idea was simple but radical. Create a permanently inhabited outpost that orbits Earth every 90 minutes. The evidence for this bold vision lies in early agreements between NASA, Roscosmos, ESA, JAXA, and CSA, signed in the 1990s after decades of competition in space. These documents show the world moving from rivalry to collaboration, proving that global cooperation can achieve breakthroughs far beyond individual capability. This moment mattered because it transformed space from a political battleground into a shared scientific frontier. It also set the foundation for a modular station, one that could grow over time and be maintained by different nations. Turning the idea into hardware required the most complex engineering design ever sent to orbit. NASA's published schematics show the ISS as a series of modules connected across a truss structure longer than a football field. Solar arrays the size of small wings provide over 100 kilowatts of power, while radiators dissipate excess heat, a critical requirement in the vacuum of space. These design documents reveal how engineers balanced mass, power, and safety while ensuring the station could support humans continuously. This engineering marvel matters because it allowed the ISS to host dozens of experiments at once, transforming low Earth orbit into an active scientific ecosystem. Assembling the ISS was an even greater challenge. NASA mission logs detail how astronauts launched nearly 30 space shuttle flights to build the station piece by piece. Modules like Unity, Destiny, and Columbus were delivered over 13 years, each requiring delicate installation while orbiting at 28,000 kilometers per hour. The process relied heavily on spacewalks, where astronauts worked for hours in pressurized suits to bolt new segments together. This construction effort is important because it demonstrated that humans can build large structures in space, knowledge critical for future Moon and Mars missions. Space robotics played a pivotal role. The Canadarm2, documented in NASA's Mobile Servicing System Guide, acted like a giant orbital crane. It moved modules, captured spacecraft, and even transported astronauts. Dexter, the robot handyman, performed delicate maintenance tasks too risky for humans. These systems prove that robots and humans can work seamlessly together in orbit, a lesson that continues to influence modern satellite servicing missions. One concept the ISS did not adopt was artificial gravity. Engineering studies show that rotating the entire station fast enough to simulate gravity would create dangerous structural stress and motion sickness. This failure is insightful. It reveals the practical limitations of current spacecraft design and explains why low gravity remains unavoidable for now. Together, these achievements made the ISS not just a station, but a symbol of what humanity can accomplish when science leads the way. Life and science in zero-G. Living in microgravity changed everything about how humans understand daily life. Astronaut diaries and NASA health studies describe how sleeping, eating, and even moving require new strategies. Without gravity, fluids redistribute, muscles weaken, and bones lose density. These observations aren't trivia. They're critical data used to prepare future crews for long-duration missions to Mars. Understanding how the body adapts helps scientists develop countermeasures like resistance exercise and improved nutrition, making microgravity research essential for deep space exploration. Zero gravity also transforms how fire behaves. Experiments conducted aboard the station and published by the Smithsonian reveal that flames burn as blue, spherical shapes rather than flickering cones. Without buoyancy, hot gases don't rise. Instead, they slowly mix with surrounding air. This strange behavior is important because it helps engineers design safer spacecraft. By understanding slow-burning spherical flames, future habitats can be built to better detect and suppress fires in space. Liquids behave in equally surprising ways. Studies on boiling fluids and microgravity show that bubbles don't rise or separate like they do on Earth. Instead, they cling to surfaces and grow unpredictably. These findings matter because they influence the design of cooling systems in spacecraft and satellites, which rely on predictable fluid movement. The ISS experiments revealed new physics that engineering textbooks had never accounted for before. Safety in orbit requires different thinking. Avoiding explosions is a serious concern in a sealed metal environment, so the ISS uses specialized air filtration, pressure regulation, and leak detection systems informed by years of microgravity research. These tools exist because experiments demonstrated how combustible materials and vapors behave differently without gravity. Understanding these differences helps prevent accidents in future stations and crewed spacecraft. Beyond daily survival, the ISS became one of the most advanced science labs ever created. The Alpha Magnetic Spectrometer, AMS, mounted on the station's exterior, collects cosmic rays that never reach Earth's surface. Data published through NASA and CERN show hints related to dark matter behavior, clues that shape new models of the universe's invisible structure. These results matter because they offer evidence that cannot be gathered anywhere else in the solar system. Quantum science reached new heights, literally. Experiments in the cold atom lab produced ultra-cold gases close to absolute zero, allowing scientists to study quantum waves, atom interferometry, and exotic behaviors impossible under Earth's gravity. These breakthroughs advance navigation systems, sensors, and the foundations of quantum physics. Orbiting experiments remove gravitational interference, giving researchers a cleaner environment to observe delicate quantum states. The ISS also transformed climate science. Earth-observing instruments monitor atmospheric composition, wildfires, ocean color, and storm patterns from a vantage point unmatched by satellites. NASA's Climate Division uses this data to refine weather models and study long-term environmental changes. These observations matter because they provide near-continuous, real-time monitoring of our planet, essential for improving predictions and understanding global trends. Together, these discoveries prove that the ISS is more than a spacecraft. It's a laboratory rewriting how we understand physics, biology, safety, and Earth itself. The final descent. As remarkable as the ISS is, its journey is nearing its end. NASA's official transition plan outlines that the station is aging, with structural stress, rising maintenance costs, and outdated systems making long-term operation unsustainable. Some components have been in orbit for more than 2 decades, far beyond their intended lifespan. This reality is important because it shows that even the greatest engineering achievements eventually face physical limits. NASA's roadmap explains how the ISS will be carefully deorbited around 2030. The plan is to guide the station into a controlled reentry over a remote region of the Pacific Ocean known as Point Nemo. This process matters enormously because an uncontrolled descent could put debris at risk of reaching populated areas. Engineers will use propulsion from visiting spacecraft and built-in thrusters to lower the station's altitude in stages until it ultimately breaks apart safely. The retirement isn't just an ending, it's the start of a new era. Several commercial stations, including Axiom's platform and the Starlab project, are scheduled to replace the ISS as the next generation of orbiting laboratories. These new stations aim to be more flexible, cost-effective, and technologically advanced. Their development is important because it transitions low Earth orbit from government-exclusive territory to a space accessible for research, tourism, and industry. Meanwhile, China's Tiangong station is expanding its capabilities and attracting global scientific interest. While the ISS represents the past 25 years of cooperation, Tiangong and upcoming commercial stations represent the future of distributed science in orbit. This shift matters because it sets the stage for new partnerships and new competition, driving faster innovation. What humanity loses with the ISS's retirement is profound. We lose a historic symbol of international unity, a unique scientific environment, and a generation of expertise gained through hands-on orbital construction. But what we gain is equally powerful. New stations designed with modern technology, better energy systems, advanced robotics, and lessons learned from every ISS experiment. These next platforms will push science further, support lunar missions, and prepare crews for the next frontier, Mars. The ISS ending is not a tragedy. It is the natural evolution of human spaceflight. Its legacy forms the blueprint for every station that will ever follow. The ISS may be approaching its final chapter, but its legacy is just beginning. Everything we learned up there, from strange flames to quantum waves, will shape the next generation of space stations, lunar bases, and deep space missions. Its retirement isn't the end of an era. It's the launch pad for everything that comes next. Thank you for watching, and don't forget to like, share, and subscribe. Your support means the world and keeps our journey going.